after this generic overview of all the things that the web application developers should fix, let's see why we have experienced those long delays when I went to the Stanford website. The first thing we'll discuss is TCP, and you know that TCP is the protocol that offers reliable stream delivery service. The emphasis is on stream. TCP does not offer block transfer or transactions. It offers you a reliable stream. It handles very well packet loss, duplication, and reordering. It does not guarantee timely delivery. It cannot support multiple parallel sessions. You need multiple TCP sessions for multiple sessions, and it does not support structured data or record boundaries. It's a stream of bytes with no internal structure. You're probably aware of the three-way handshake that TCP is using. Whenever a client wants to connect to a server, first thing it sends the TCP SYN packet, and the server responds with SYN plus ACK, so they establish the sequence numbers, and the client responds with ACK packet plus the first data packet. You see, we need one round-trip time to get from the client to the server and back. So we spend one round-trip time before we can send the first data. This is the 192 milliseconds that I was experiencing in the connecting phase. Is it really that far to Stanford? Well, I did some pings, and not surprisingly, these two numbers match. Then I did a trace route. I'm from Europe. And you see, I spent 22 milliseconds getting to Frankfurt, and then 30 milliseconds got me to Paris. Then I needed 80 milliseconds to get to the first transatlantic hop, and 70 milliseconds across US, and so on and so on. In the end, 192 milliseconds to get to Stanford from Central Europe. So yes, it is that far to Stanford. By the way, all these times are round-trip times, so not one-way times. In theory, this was provided by Wolfram Alpha. You can ask that magic program how far it is from somewhere on Earth to somewhere else on Earth, and they give you the distance, and they give you the time it takes for light in fiber to get from here to there. Their calculation, as the crow flies, is 45 milliseconds. In reality, you see it's almost 200 milliseconds. So there's a huge gap between theory and practice. But that's not all. Then I did some local tests. And from my home over the VPN tunnel, I was pinging the website of my company. With the fiber connection I have, it took 8 milliseconds to get to my company's website. Then I switched over to 3G. So I connected to the internet over my mobile phone using the exact same laptop, did the pings, and you see the results are all over the place. I'm told that this is caused by the need to set up radio channels in 3G network, and supposedly, if you surf a lot, the time will drop down to approximately 100 milliseconds, but usually not below that. If you do pings, then there is no constant traffic, so the radio network has no need to give you more channels, and therefore the ping times stay as high as they do. If you're surfing, it's better than this. Anyway, we spent one round-trip time, which in mobile networks could be something like 100 milliseconds, just establishing the connection. By the way, remember, latency is never zero. This is one of the things that the application developers always forget. So the first TCP SYN packets were sent, and TCP session was established. Now I'm sending HTTP request and getting response. Yet again, here we have another round-trip time. This is the waiting phase, which when I was connecting to Stanford took another almost 200 milliseconds. So you see, I've spent 2 round-trip times before I got the first byte of data. Not only that, In HTTP request and response, there are numerous headers, and worst case, you generate so many cookies on the client side that all these cookies don't fit into the first burst of data. If you can't send the request in one burst, and the burst is approximately 4.5K, then you will spend an extra round trip time just to send the request. Then TCP congestion window kicks in. TCP was developed in 1980s. In those days, they were fighting problems like congestion and buffer memory utilization and very slow links and so on and so on. And TCP has extremely good mechanisms to handle that. It has windowing, where we know how much buffering is available on the receiver end, so we don't overload the receiver. And it has something called congestion window, so that we can test how much can be sent without congesting the network. Congestion window is always less than the window size, and it's the window size reduced to avoid congestion. Initial congestion window, because we have no idea what the network conditions are, is by default 3 packets. In standard networks with MTU being equal to 1500 bytes, that would be 3 times 1460 bytes, or approximately 4.5K, a bit less than that. If you have networks with lower MTUs, then of course 3 packets are a bit lower than that. In the first response, the server can deliver approximately 4.5K worth of data. After that, the server has to wait for the first ACK packet to arrive, and then it can send one more packet. When the second ACK packet arrives, it can send one more packet, and so on and so on. So you see, another round trip time lost. We're already at 3 round trip times, or in my case, we are approximately here at 600 milliseconds, and we still don't have the whole website. We only have the first 4.5K. Then it took a little bit longer, you see here, for the whole web page to arrive. And this is just the first page. Now the browser knows what other elements it has to start downloading. So you see, it takes way longer than the 100 milliseconds that should be our goal. Speaking about TCP congestion window, Jeremy Stretch did a great test, and this is straight from Wireshark. So you can do the same thing. Start a file transfer in Wireshark, capture all TCP packets, and then there is a graph in Wireshark that you can generate. And you see, in his case, you see that the packets appear at 50 milliseconds, 100 milliseconds, 150 milliseconds, and so on and so on. That means that for him, round trip time was 50 milliseconds. First, he gets 3 packets, then he gets a bit more, and so on and so on. And data really starts flowing after approximately 8 round trip times. At that point, he was hitting the actual window size on the client or on the server, whichever is smaller, probably on the client in this case, depending on how he was doing the file copy. And from here on, there are no more stops. Data is flowing continuously. So at 8 round trip times, he was able to fill the pipe, the bandwidth. He was no longer delay bound, he was bandwidth constrained. After 8 round trip times, or in his case, 400 milliseconds. For me, the round trip time was 200 milliseconds, so 8 round trip times would be 1.5 seconds. And also, don't forget that TCP is very sensitive to packet loss. Another graph from Jeremy, he published this on my wiki, so here's the URL at the bottom. What he did was he was configuring either policing or shaping on a router interface, and then he ran 4 TCP sessions over it. As you can see, with policing, which is actually packet drops, the moment packet is dropped from one session, that session reduces its bandwidth considerably. And so on, and so on, and so on, and so on. So you get this totally unpredictable curves. By the way, black is the summary, and the other colors are individual sessions. you see that some sessions don't even start well because of packet drops and pick up later on, for example, the blue one. The point of this picture is that the moment you start experiencing packet drops, performance of a single TCP session becomes totally erratic. On the other hand, if you're delaying packets, so if you're shaping, not dropping, the performance is optimal. Because TCP responds very well to delays, it says, okay, I'm experiencing delays, must be congestion, let's reduce the sending rate a bit. Whereas if you drop a packet, you go back to slow start and all sorts of interesting things happen. Let's recap what we've learned so far. The web load time is heavily influenced by TCP and HTTP. We need one round-trip time to establish the session, second round-trip time to send the request and get initial response data, and third round-trip time if the resource is more than 4.5K in length. The moment we get packet loss, we slow down. What can be done? There are numerous things you can do. For example, browsers use parallel TCP sessions. On the other hand, if you already have TCP session, it's better to reuse existing TCP session than to establish a new one. So with persistent HTTP connections, browser can reuse a session that was already established, so we save one round-trip time, plus we have a bigger congestion window because the session was already used. The next thing some browsers do is they pre-establish TCP sessions. So the moment you start loading a web page, the browser would, in the background, open parallel TCP sessions so that, yet again, we get rid of the one round-trip time. And there are things you can do on the server side. Google, for example, is recommending, and they're doing it, that you increase the initial congestion window to 10. This is not a problem. You can do this and nobody will notice, apart from your website being a bit faster. The other thing Google is proposing is to use TCP fast open, which is TCP SYN packet that carries data. That thing is tricky and will probably have significant problems with some firewalls. On the other hand, one thing that is totally underestimated, apart from big corporations that know what they're doing, use content delivery network. This thing used to be expensive. Right now, you can get content delivery network from Amazon for a few dollars a month, depending on the traffic. So if you have users that are on different continents, it does make sense to invest in Amazon's or whoever's content delivery network. To get more information about my webinars, to register for an online session, or buy a recording or the yearly subscription, please visit my website.